So there are actually two equations that you need to know, and with these two equations you can calculate just about anything you want to know about a photon of electromagnetic radiation. One of these fundamental they're not really particles in the classical sense, but they're fundamental packages of energy that constitute what is being propagated in electromagnetic radiation. And the electromagnetic spectrum has wavelengths, some of which are very, very large. We call these radio waves. And as they get smaller, they fall into the category of microwaves. And as they get smaller still, as the wavelength gets smaller still, then these microwaves become infrared rays. And then we get into a very, very narrow band, which is actually the visible band, that starts out goes from the red down to the violet, which is shorter still, but that's in that little narrow band. That's what we can see. And then if we go beyond that, we get into the ultraviolet. And the ultraviolet starts out as long wave, and then it becomes mid wave, and then short wave, and there's something called vacuum UV, which is very, very short wave ultraviolet radiation. This is where we start to get into the area of ionizing radiation. These are forms of radiation that will actually cause atoms, for instance, to lose electrons. They're powerful enough to actually kick an electron out of an atom and cause it to ionize, to become an ion. And if we go shorter still, we'll get into that region of the electromagnetic spectrum that is known as X radiation. We already talked about that. And the shortest wavelength of all, gamma radiation. So these are all forms of electromagnetic radiation. And we have these two equations. One of them says C equals lambda times nu. I'm going to erase my wave so I can put these equations on the board. Apologize for the small board. I'm actually doing this in my home office. So this is the only blackboard or green board that I have available. C equals lambda times nu. So what does that say? What is C? C is actually the velocity of electromagnetic radiation in a vacuum. So when light or any other form of electromagnetic radiation is propagating, is moving through a vacuum, basically this is a constant value, and it's 3.0 times 10 to the 8th, sorry about that, 10 to the 8th meters per second, or 3.0 times 10 to the 5th kilometers, thousands of meters per second. So that's the value of C. That's a constant. Lambda is going to change, and frequency will change, but the two of them are reciprocally related. And since lambda is going to be measured in meters, or actually usually it's nanometers, which are billionths of a meter, and remember that frequency is measured in reciprocal seconds. That's 1 over second. You're going to get you're going to find out that you're going to have you're going to be actually getting a velocity out of that. It's going to be a distance divided by a time. Nanometers per second would give us that value. So we can actually, what this tells us is that since this is a constant, if we know lambda, we can find the frequency by dividing the velocity of light, or of electromagnetic radiation, by lambda. That will give us the frequency. And if we know the frequency, we can find the wavelength by dividing it by the velocity divided by the frequency will give us the wavelength. Okay, so that's the first equation. And the other one is actually the one that relates the frequency, nu, to energy. So if we want to find out what the energy of a photon is, the energy is going to be equal to h times nu. Again, the frequency. So what is nu? I could make a joke and say, I don't know, what's new with you? But I won't do that. We'll just say nu is, we already said that nu was frequency. What is h? H is something called Planck's constant, named after, again, a very famous physicist by the name of Max Planck. Don't remember whether there's a K on the end of that or not. I think there's a K. Planck's constant. And this has a value of 6.636 times 10 to the minus 34th joule seconds. A joule is a fundamental unit of energy. So when we want to find energies, if we take joule seconds and we multiply that by frequency, which is reciprocal seconds, 1 over seconds, seconds will cancel out, and we're going to be left with the energy in joules. So this, we multiply, if we have the frequency, if we have lambda, but we don't have the frequency, we can use lambda and c to find the frequency. So since we know that nu is equal to c divided by lambda, we could also write this equation in another form, and we could say that E equals hc divided by lambda. So we have this constant, we have that, and this is a constant, that's a constant, and that's lambda. So what that tells us basically is, since these are both constants, is that energy is actually inversely proportional. Let me erase this now. Energy is inversely proportional. This is a proportionality. This symbol here is a proportionality symbol. It's inversely proportional to wavelength. That is, that it's proportional to 1 over the wavelength. Okay, so that's what we do with those equations. Now let's move on, and let's look at atomic structure. And we talked a little bit about the atomic structure already. So we know about electrons. We've already talked about that. Electrons are small. They're approximately, if we look at, I said protons and neutrons are about the same size. The electron is approximately, has a mass that's about 1 over 1,000. I think the number is something like 1,837 seventh the mass of a proton. So it's quite a bit smaller than a proton. Almost 1/2000th the size of a proton or a neutron. Okay, so it's very, very tiny. And if we wanted to look at the atom itself, if you imagine you're inside a football stadium and you take a marble about so big and you stick it at the right dead center on the 50-yard line, the electron is going to be about the size of a mosquito, and it's going to be buzzing around somewhere in the stands. And the rest of that is basically empty space. And that's, if we looked at a hydrogen atom, which consists of only a single proton and an electron, that's about the scale. That's about the scale of that kind of thing. But with larger atoms, anything besides hydrogen, we're going to have, we'll also have neutrons in there as well, and we'll talk about that in a moment. So we have protons and neutrons and electrons in every single element, with the exception of hydrogen, which is just a proton and an electron. But there are some forms of hydrogen that also have neutrons in them. So for instance, there is a form of hydrogen, we call the common form of hydrogen, which is most of the hydrogen that we have here on Earth. Probably certainly over 99% of it is in the form of what we call protium, and protium is written like this. I'll talk about these numbers in a moment. This is what we call isotopic notation. We'll talk about that in a minute. So this is called protium, and we have another form that's called deuterium. And there's a third form of hydrogen called tritium. Now, outside of protium, everything else in the universe has neutrons in it. This is the only one that has no neutrons. This number down here on the lower left-hand side is what we call the atomic number. It's actually giving us, it's telling us the number of protons that are actually in this particular element, in this particular atom. The number up here is what we call the atomic mass. And the atomic mass is the sum of the protons and the neutrons. And since there are no neutrons, 1 plus 0 is still 1. So we get that. Now we have this other, and by the way, these things are referred to as isotopes. they're the same element. They have the same atomic number, but they differ in the number of neutrons that are in there. So there's 0 neutrons here. 2 minus 1 gives us 1 neutron. This is 1 proton, and since the atomic mass is 2, that indicates that there must be another particle in there, which is the neutron, which also has a mass of 1. So if we subtract that from that, we'll get 1. That tells us that there's a single neutron in there. And this is another form of hydrogen that's present on the planet, and you can actually isolate this. For instance, you can get this from water. If you have water in a storage battery, it turns out that water, H2O, has a boiling point of 100 degrees Celsius. But this also has sometimes, we use the symbol D in place of that. If we're not writing it in isotopic notation, as I said, these things are called isotopes. That is, they have the same number of protons, but they differ in the atomic mass. They have different numbers of neutrons. So these are isotopes. So this is isotopic notation. But this other form is just a quicker way of abbreviating this. So we have D2O, which is called deuterium oxide. Looks just like water, would probably taste like water, would be very, very dangerous for you to consume for reasons that I'm not going to go into right now. But this has a boiling point of about 101.5 degrees. And it turns out that when you have a storage battery, which is one of these sulfuric acid batteries, and there's water in there, the water evaporates more rapidly than the deuterium oxide that's naturally present in the water does. So older storage batteries tend to have a higher concentration of deuterium oxide. And I've known people that have actually taken the water acid mixtures out of these things if they're old, and attempted to separate these things by distillation. And you can purify. I mean, you can also buy deuterium oxide. It's probably an easier way to get it, but it is fairly expensive. You might have to pay $1 a gram in order to get pure deuterium oxide. But these are what we call stable isotopes of hydrogen. And there's a third isotope, which called tritium, that has 2 neutrons, and it's radioactive. It is not a stable isotope. So we talked about isotopes, we talked about electrons, we talked about protons, we talked about neutrons. Anything that's in bold in your textbook is important, and when I make up your exams, I'm going to look at the bold, the things that are bold in your textbook, and that's probably where I'm going to get a lot of my questions from. And your book defines something called a nuclide as an isotope of any element, any isotope of any element. And specifically, we're going to be dealing with a lot of what we call radionuclides. So the radionuclide is an isotope of an element that happens to be radioactive. So these are all nuclides. Protium, deuterium, and tritium are all nuclides. They're all isotopes of hydrogen. But tritium is actually a radionuclide because it is radioactive. Okay. We talked about mass number, which I called atomic mass. Your book calls it mass number. It's the same thing. And I also talked about atomic number. And there's a third thing in here. In isotopic notation, you don't usually see it, but if we write, just as a general form, we want to write an element. We can write it in this form: X, N, Z, and A. So I've already explained to you what Z and A are. Z is the atomic number. That's the number of protons. A is the atomic mass, or the mass number. And N, which if we wanted to put it in, it's not usually done in isotopic notation. You don't usually put that. Usually you only put these two in. Because you can figure out what N is. So that it's not necessary to put this other number. Because what is N? N is the number of neutrons, so we could put it in here. But the number of neutrons, N, is just A minus Z. So we can say Z plus N equals A. Your book states it as A equals Z plus N, but N, in fact, is then A minus Z. So you can see that. So you should know that, and that's how we can determine, if we have this written in isotopic notation, we can determine the correct number of particles. Okay, a couple other terms that are not commonly used, but you should know them anyway. Something we talked about isomers, isotopes rather. We haven't discussed these other two. One of them is isotone, ISOTONES, and these are nuclides where the same number of neutrons that have the same number of neutrons, but a different number of protons. So here, they would have the same N, but what would be different would be the Z numbers. So they would actually be the examples of that. Let's see if we have an example here. Yeah. So oxygen 16 and nitrogen 15, which are shown midway on page 3. Oxygen 16 is has 8 protons, 8 neutrons, and a mass of 16, and nitrogen 15, which still has the same number of neutrons, that is 8, but it's got 7 protons and it has an atomic mass of 15. So the difference is that 8. So those things are referred to as isotones, and there's one other thing which is an isobar, and these have the same mass number but differing numbers of protons and neutrons. So the example given here is oxygen 18 and fluorine 18. And if you look at those two, oxygen 18 and fluorine 18, you'll notice that the number of protons and neutrons are different, but they still, both of them sum up to 18. So they're different elements. Okay. Collectively, neutrons and protons are referred to as nucleons, as your book points out. And I'll probably have more to say about this later. I don't want to really spend a lot of time with this. The nucleons themselves, with the exception of electrons, which are a class of particles that are referred to as leptons, the other particles, the protons and the neutrons, and there are a number of other particles as well that are not normal constituents of matter, but they are particles that are investigated in high energy physics, things like mesons. These things are actually composed of smaller particles that are called quarks. And we'll need to understand a little bit about the quark in order to understand radioactive decay. So let's talk a little bit about that. And so there are different kinds of decays that actually occur in nuclear physics. And there is one form of decay that's known as alpha decay. And in alpha, well, actually, I think I probably want to discuss beta decay first, because I mentioned before that beta particles were electrons that are emitted from the nucleus of an atom. And again, you have to ask yourself the question, well, how can that possibly happen? Because electrons are not actually in the nucleus. And that's true, they're not there, but they actually can form during this particular kind of transformation. So in the case of let's see, how do I want to tell you this? Well, I think we have to understand something about the quark and about subatomic particles. So if we look at a neutron and a proton, let's do the proton first. So here's a proton, and here's a neutron. And these consist of smaller particles called quarks. And both the proton and the neutron have 3 quarks. Now there's 6 different kinds of quarks. Well, if I count what are known as antiparticles, there's actually 12 quarks. But I'm only going to be concerned with 2 of them. And these are called up quarks and down quarks. So the proton consists of 2 up quarks, which I'm going to abbreviate with U, and 1 down quark, a D. And the neutron has 2 down quarks and 1 up quark. Okay? So what actually happens during what we call beta decay, which is the production of this electron, the beta particle is an electron that actually is fired out of the nucleus of the atom, is that one of the neutrons, in this case, actually converts to a proton. And it does so in this fashion. One of the down quarks actually flips and becomes an up quark. So if that happens, if down goes to up, then what happens is neutron goes to proton, when the down goes to up. A couple of things I want to tell you about this is that unlike most particles we think of it as having integral charges, +1, +2, etc. These actually have fractional charges. So the charge on an up quark is +2/3, and the charge on a down quark is -1/3. Well, that's kind of interesting because if you take two up quarks and you add these up, you've got 2/3 plus 2/3 minus 1/3. That's 4/3 minus 1/3, which is 3/3, so that equals 1. And lo and behold, that will give you a charge of +1, which is the charge on a proton. Now, we do the same thing for a neutron. It's got two down quarks, -1/3, and another down quark, -1/3, and it's got an up quark, +2/3. So we've got -2/3 plus 2/3 equals 0, and the charge on a neutron is 0. It has no electrical charge. So that's where the charges come from. Now, the other thing that I need to show you is what actually happens in this reaction where a neutron becomes a proton. And why should that actually have to happen? We'll talk about that in a minute. Okay, so here we are. Stabilize my board before it falls over. And let's see if I can find a little example for you here. Okay, so we've got, here's an example. It's carbon-14. Carbon-14 is a commonly occurring radioisotope. It's a radionuclide of carbon. The normal form of carbon is called carbon-12. So what does carbon-14 have? I'm actually on page 4 right now. And so here's your carbon-14. And what happens is, again, one of the 8 neutrons that's in here is going to flip. One of its quarks is going to flip, and it's going to become a proton. So when that happens, it's going to go to an element that where the number of protons is now going to be 1 greater, but the atomic mass will not have changed. We really haven't changed the mass. So it's going to be an element which is going to have an atomic number of 7 and an atomic mass, or a mass number of 14. And if we look at our periodic table, you'll find out that that's the element nitrogen. So what we can say is that carbon plus, well, it can be shown in a number of ways. We can just show it this way. And we can say that carbon is going to go to this plus a beta particle, which is sometimes written this way, beta minus, to show you that it's a negatively charged. Or it could be written as an electron. And when we write this, it's written in this fashion, -1 and 0. Now that may look pretty peculiar to you, because you would say, how can you have a negative atomic number? Well, you do, because what you want, when you actually do this, you're forming an equation where everything on the top has to sum. I'm going to take the beta out of here and actually put this electron back in here, -1 E0. So if I take the subscripts in here and I add them together on one side of the equation, I have to get the same subscript that I have on the other side of the equation. So 7 minus 1 is 6, and 14 plus 0 is still 14. So this balances out very nicely. And that's the equation that you actually see on the bottom of the page. It's missing one other little thing. So we know that when carbon-14 gives off a beta particle, which is what's happening here, it's producing nitrogen-14 and a beta particle. There's another particle. Your book will talk about it later on. It doesn't mention it right here, but there's another beta particle, and we use that nu that we use for frequency. We use that same symbol to represent this particle, and I put a line over the particle. The line means anti. So this is what we call an anti-neutrino. This is a really tiny particle, much, much smaller than the electron. It doesn't even enter into the mass calculations. But to be technically correct, we would say the carbon-14 goes to nitrogen-14, produces a beta particle and an antineutrino simultaneously. Okay, so that is kind of a quick and dirty explanation of beta decay. And then I want to talk a little bit about alpha decay. There are certain other elements that will actually, when nuclei get too big, one of the things that I wanted to mention, even before I do that, is that if we look at the ratio of, basically, if we're looking at the ratio of neutrons to, I don't want to get ahead of myself. Wait a minute. Before I even do that, a couple other things that I missed here. I was talking about quarks. Oh, I didn't talk. There's two fundamental forces that I didn't talk about. There actually are four fundamental forces in the universe. One of them is the electromagnetic force, and we were talking about that previously. Electromagnetism, everything from radio waves down to X-rays or gamma radiation, visible light, all these other things are electromagnetic radiation. So we call this the electromagnetic force, and there's a fundamental unit of that, which we call the carrier of the electromagnetic force, and that's the photon. So we have electromagnetic force, it's carried by the photon. There's also something called the gravitational force, and there is a what I would call right now a hypothetical or theoretical particle that is the mediator of that, although no one's ever actually been able to observe it, but all of our calculations tell us that according to the current theory, there should be such a particle, and it's referred to as the graviton. There are two other forces that we're going to be really interested in. One of them is a very, very short range force. It's a very, very powerful force, but it only acts at a very, very short distance. Something on the order of 10 to the minus 15th meters, 1 femtometer. If you get any further away than that, the force basically, unlike gravitational force, which actually diminishes in a predictable way with the square of the distance that the two things are from one another. And that's also true of electromagnetic electrostatic forces. They also diminish in the same way. Not true of the force that actually holds protons and neutrons together in the nucleus, and that's called the strong force. And the particle that mediates that is something called the gluon. And these actually have been observed. So we have the gluon holding these things together. Now that's the strong force. There's still another force which is referred to as the weak force. And this is the one that actually mediates radioactive decay. It's a much, much smaller force, and it's mediated by a number of particles that are referred to as vector bosons, B-O-S-O-N. So you'll have things like the W boson, W plus boson. There's a variety of these other particles that are actually exchanged during this radioactive decay. And it is actually the boson itself that's supposed to give rise to the beta particle and the antineutrino. Okay. Gluons and bosons. All right, let's see, what else do we have in here? So alpha decay. Basically, some atoms, when we get to atomic numbers above 83, which is the element bismuth, we find out that there are, for all the nuclides that are known, they're all radionuclides. There are no stable isotopes for any element beyond element 83. All of them are radioactive. So eventually you get to a point where apparently the nucleus has become so large that it no longer is cohesive anymore. In other words, it needs to reach a certain smaller critical mass in order for it to actually have some stable isotopes. So in order to do that, it starts shedding little pieces of itself. And these are alpha particles. And I mentioned before that the alpha particle, alpha, this is the Greek letter alpha. So alpha particles are the nuclei of helium atoms. So if you look at the helium atom, using the Bohr model, we've got 2 protons, 2 positively charged particles, 2 neutrons, which have no charge, and then we have 2 electrons. That's the atom, If we strip off the electrons so that we just have the nucleus, that is an alpha particle. 2 protons and 2 neutrons. So by losing 2 protons and 2 neutrons, an element such as uranium 92, 238 is actually going to lower not only its mass number, but it's also going to lower, I'm sorry, its atomic number, but it will also lower its mass number as well. It'll lower this one by 2 and this one by 4, and so it will form 90, and we'll put an X in there, 234, and if we look that up, we'll find out that that's the element thorium. And that produces an alpha particle, which is either written this way, or we could write it as helium-2, 4. But again, everything has to sum up on both sides of the equation. So if I've got a 4 here and a 234 here, that's going to give me 238 over here, and a 90 here and a 2 here gives us 92. So the atomic numbers sum and the atomic masses sum as well, and we get the correct correct mass. So these are 2 common forms of decay, alpha decay, and the other one that I mentioned, beta decay, which is sometimes referred to also beta. So beta decay is also, it's either beta, or sometimes it's referred to as negatron decay. And you might imagine if there's a negatron decay, maybe there ought to be the opposite of that. And that's something called positron decay, and in fact there is. So where beta decay occurs is with lighter elements where the ratio of neutrons to protons is starts to get much greater. Well, it starts to deviate from the point where we would actually expect to have stability. And there's no really exact number that I can give you for that. Generally speaking, when the ratios become greater than 1.5 to 1, that usually is a point where things start falling apart, but sometimes it's even below that number for some of the lighter weight elements. So basically, we'll get beta decay as we start to see more and more neutrons with respect to the number of protons that we saw. You know, for instance, as I mentioned before, with carbon-12, you have the same number. You've got a 1-to-1 ratio. Then you go to carbon-14. Carbon-13, by the way, is still, it's another nuclide, but it's still stable. It has 7 neutrons. But once we get to 8, which is only a ratio of 1.25 to 1, carbon-14 becomes radioactive.